Okay, so so if we do integral, say I'm going to integrate this from 0 to 6. We need to first of all know what is that integral going to mean. That we're going to get a value. What would that value mean in a geometric sense? What would that value mean in a geometric sense? And I don't need any calculations yet. I just want to know. So when I get this, if I do this integral and I get this answer, what is the meaning of that answer relative to geometry?
Second area minus the first
Yeah. So do you want to try again, and without doing the calculations? Yeah. So what will it mean?
So the bigger area minus the smaller area will give us the net area.
Right. So an integral will always give us net area. Anytime the function is above the x-axis, that will make a positive contribution to the total value of the integral. So we truly get area in that case. Whenever the function goes below the x-axis, that will make a negative contribution to the total value of the integral, or it will add the opposite of the area. Right? So areas are always positive, but whenever the function goes below, it will contribute to the integral as a negative value. So this answer then would be, if I call this, say, A1 and A2, and whenever I write capital A to mean an area, that will always be a positive value, so this integral would compute what? A1 plus A2. That's what this integral will compute. Agree with that? Nope, it's not A1 plus A2. It's A2 minus A1. Where these areas are positive, right? So that the integral will always subtract or take the opposite of any area that's below the x-axis. Okay? So that's the concept behind this. So if we wanted this total area, what integral expression would we need to actually get the total area? Yeah, Christiana. Okay, but then I want to evaluate that, and I don't know how to evaluate an absolute value, so what could I do? What expression could I set up that I could actually evaluate to get the total area? And what integral expression would get me A1 plus A2? Yeah.
So it would be the area of a semicircle, which is the area of the circle divided by 2.
Okay, but
So that would be the amount function.
I want an integral expression that would get me the total area, A1 plus A2, yes.
The integral from 0 to 2 plus
Zero.
integral of 2 to 6.
Okay, integral, this is what I heard you say, integral from 0 to 2 plus integral from 2 to 6. I don't want to use absolute values. I don't want to just use absolute values. So would this work? This would be exactly the same as this.
You can do the second one minus the first one.
Hold on. Whoa. Okay. This expression right here, integral from 0 to 2 plus integral from 2 to 6, you need to see that that's exactly the same as what integrating from 0 to 6 does. So we can split it up and add them up all day long, but what we really need is, so this will not give me a positive value, right? This is going to give me the opposite of A1. So if I need this to be, if I want to get the total area, A1 plus A2, then many of you were saying, I need to. Well, what do I need to adjust here? Make the first integral take the opposite of the first integral. Because that first integral is going to give me a negative value, the opposite of the area. So I need to take the opposite of that to get the actual area. And then if I add that, then I'll actually get the total area. So this is the concept behind it. And so if we really understand this, then these questions that they ask us should be a breeze. Yeah.
So we know that area is a positive number.
Uh-huh.
But I guess we need to think about A1 then when we're using kind of integrals that are below the x-axis.
Uh-huh.
It is a negative area.
It's the opposite of an area. Think of it that way. There's no such thing as a negative area.
But it is always going to be the opposite.
Yeah, so anytime that any area that's carved out below the x-axis, that part will have a negative contribution to the total integral. And so it's the opposite of the area.
Is it grammatically incorrect to write the for the first interval there, the integral from 2 to 0 and remove the negative sign?
You could do that too. That's another way to do it. You could do 2 to 0. So that would also get it.
Do you
So
have a preference? Or?
I guess not. This is you're kind of so it's like you got two different things causing a negative, and then they cancel out, right? So it's okay, I guess. Question.
Okay. If you evaluated the 0 to 2 fx dx
Uh-huh.
without the negation,
Right.
wouldn't that give you a negative number?
Yes, it
And
would.
You're saying that negative is going to make it positive.
Yes, this integral right here that I'm putting a box around is negative. It's the opposite of area A1. It's the opposite of this shaded region.
Oh, I see what you're saying.
And so then if you take the opposite of it, it'll...
No, I got it. I'm sorry. I thought there was going to be a negative. I didn't see that there wasn't a negative sign in front of the A1. Never mind.
You didn't
If
see
there
that
had been a negative in front of the A1, then that would not be true, and I didn't see that.
over here?
Yeah.
Okay. Yeah, so total area, I just want to add up A1 and A2, which means I have to take the opposite of that integral.
Sorry.
You're good? Other questions? Okay, so I think that discussion kind of takes care of this. So when you look at these, you just have to see it through that light. All these constants, you can just pull them out in front and multiply at the end. Now for this particular one, this particular problem, say, okay, so let's just do, what should we do? C? I heard C. Let's do C. So from 1 to 4. 1, 2, 3, 4. 4 times. Okay, so we're going to go from 1 to 4. And it's going to be 4 times f of x. Well, that's just the same as 4 times f of x dx. So, what will this integral give? What will that integral give? The integral from 1 to 4, just conceptually, right? So I'm not talking about any numbers or any math, but or doing any computations. But from the integral from 1 to 4, what will that value be? Yeah.
Could you write it as A2 over 2 minus A1 over 2?
Okay. So I originally called this A. So this now, for my original, that would be A2 over 2. And this would be A1 over 2. And so you're saying what I put in the box would be A2 over 2 minus A1 over 2.
Yep.
What do we think? Exactly right. So it's going to be this quarter circle minus, or the area of this quarter circle minus the area of this quarter circle. And then we're going to, at the end, and when we get that all done, we'll multiply by 4. So we can just use geometry to do that. So the radius of A2 is 2. The radius of A1 is 1. So what's a quarter of this circle? It'd be 1/4 pi r squared. And then a quarter of this circle would be 1/4 pi times 1 squared. And then that whole thing times 1. 4. Sorry, whole thing times 4. From that's 4. So the positive quarter circle, the big one, area, minus the smaller quarter circle area. So that would be C. Any questions on this one? We should move on. Okay. Let's look at this next one. I got it. That was that one. 5. Okay. So this one caused some confusion. It's a good one. So we've got this just a line here. 4x minus 1. So that's going to be something like this. That's supposed to be a line. Let me try one more time. Sometimes a little. So here we go. 4x minus 1. Let's see if I can do better here. Okay, better. Okay, so then negative 2 to 6. Okay, now notice what they're asking for. What are they asking for? They're not asking for the integral, they're not asking for the net area. What are they asking for? The area. They're asking for an area. Which means I can't accomplish this with one integral. I can't accomplish this with one integral. If I'm going to do an integral, if we're going to use, there's two ways to go about this. I can use actual integration and antiderivative, or I can use geometry like we did with the circles and do some triangles. Okay? So which do you prefer? Should we just use geometry, or should we use actual integrals? Let's do geometry. Okay, so we'll use geometry. And so the area from negative 2 to 6 is going to be concerning this right here. So remember that you always go from your function all the way to the x-axis. You always go from your function all the way to the x-axis, okay? Not to the y-intercept. Okay, all the way to the x-axis. So that I've shaded it in red. So what will our approach to this problem be if they want the area? They're asking for the area. Are we going to do, so if I call this, again, if I call this A1 and A2, is it A2 minus A1? No, they want area, so they want A1 plus A2. So if I were to integrate from negative 2 to 6, it's not going to be right because it's going to subtract those areas. It's going to be the difference of areas. So it's asking me for areas, so I need to add them up. So what is this? At negative 2, we're at negative 9. Check my math. And at 6, we are at 23. Check my math before I start doing stuff. Okay, so what is area 1? 1/2. Base times height. So I'll use, what is this? Where does this hit? Is this 1/4? Oh, thanks. So that the x-intercept is 1/4. So we're going to do 1/2, 2 1/4, or 9/4 times 9. That's the area 1, right? 1/2 base times height. 9/4 from negative 2 to 1/4, and then the height's 9, plus A2, 1/2, base times height. Base is going to be 5 3/4, 23/4, times height, 23. So that's a geometry approach. And we can only do that because we have a nice, like on the previous problem, we had circles, which we know the formula for. And here we have triangles because it's a linear function. So we know the geometry formulas. But as soon as we get a parabola or any other type of curve, then we need integration, right? We need integration to get those because we don't have these other geometry formulas for other shapes readily available like we do triangles, circles, rectangles. So does this make sense? Did I do the math right? Let's check it. 0.5 times 81 over 4 plus 23 squared over 8. Anybody have a question? Okay, and let's look at a couple more here. Okay, so this one I have fired up on my grapher. So this one is, it says the area enclosed by 3 sine x and 2 cosine x from 0 to 0.3 pi. So I graph that. situation, and that's what this looks like. So between the purple one is sine and the red one is cosine. So between those two, from 0 to 0.3, and so there's something different about this. What do you notice? We got to get a good picture, but then what we notice is halfway through there, the curves intersect, and so we have a different top versus bottom function. So we're going to have two different typical strips. So here's our first, which is only good to whatever we find this intersection point to be. And then after that, our typical strip is different because the upper function is different from the lower function. So this was, the red one's the cosine, 2 cosine x. The purple one is 3 sine x. So what will our typical strip for this first one be? So base times height. Base is delta x. Height is, so is the height an x value, a change in x, a y value, or a change in y? So these heights and these dimensions of these elements that we're always going to ask that question. Is it an x value, a y value, a change in x, or a change in y? So for this one, it's what? It's a change in y, right? It's a change in y. So we're going to do y2 minus y1. So what is y2? Okay, and that y2 is our 2 cosine x, and y1 is our 3 sine x. When you come over here, your typical strip is going to be the other way around. So this one is, this is the first one, delta x is going to be, our y2 is our 2 cosine x minus 3 sine x. That's for this one here. And then this one here will be just reversed, right? Because now it's still going to be a change in y, but it's going to be the 3 sine x minus 2 cosine x. How are we going to find this x coordinate? Set what equal to each other? We need the y values to be equal, right? So we're going to set y values equal, find the x that makes the y the same, right? So that's simply going to be 3 sine x equals 2 cosine x, which turns out to be tangent x equals 2/3. So we got the inverse tangent of 2/3, arctan of 2/3. So our integral is going to be from 0 to arctan 2/3. Our typical is going to be this, 2 cosine minus 3 sine dx. And what is that right there? That's our base times our height of our typical strip, right? And then we're this integral just means sum up all the areas of the typical strips. Okay? Meaning is important. And then from arctan 2/3 all the way to 0.3 pi. That was my problem. And then now it's going to be, the higher one was 3 sine x. 3 sine x minus 2 cosine x dx. Okay, so anybody have a question? Please ask if I lost you. So you got to be on. So the picture is going to be really important. That we can know exactly what region it is that they're asking us to find the area of. Sometimes those regions have to be split up into 2 parts, like this one, because typical strip changes at that intersection point. Last chance on this one. Okay, last one is, I think, the last one. Yeah. So here's one, and then some of you, so this region between these two curves, for some of you, that region ended up maybe some in negative y territory and some in positive y territory. So I have an example of that. This one ends up all being in positive, but I kind of adjusted it to show you that case where you get part of it above and part of it below the x-axis. So let's take a look at that. Okay, so here's the situation. And so they want the area between these two, like this. And so we notice, though, this is all in negative territory and this is all in positive territory. So do we need more than one typical strip? So if we look at this, so I could draw my typical strip like this. Now, as I go from left to right, does that typical strip, the definition of that typical strip change? All the way from the starting, so the first one will be here, all the way to the last one will be here. So I'll just draw a few along the way. And now we're piercing up into positive y territory. Is there just one typical strip we can use for the whole region, or do we need more than one? So let's talk about it. So area of a typical strip, space times height, we know. How about the base? Does the base change, or is the base the same for all of them? And it is delta x, right? Delta x. Okay. So now the height of this. These heights. Are they an x coordinate, a y coordinate, a change in x, or a change in y? Are they all a change in y? They are all a change in y. So we can say delta x times y2 minus y1. Now that difference, this will always be a greater y value than this one. Whether they're both positive, whether one's negative, whether they're both negative, y2 is always the higher y value, and when you subtract y1, you get that positive height. Okay, so like down here, if it was -2 to -4, if you took -2 minus -4, what would you get? +2 height, right? And what about here? If you took -1 minus, or sorry, +1 minus -1/2, would you still get the height? Yeah, if you took 1, and this was, say, -1/2, that height would still be 1 minus -1/2, 3/2. And down here, -2 minus -4 about will give you a height of +2. And up here, 4 minus 3.5. So what what's 3.5? 7/2? Equals 1/2. So what I'm trying to show you is that when you're doing this y2 minus y1, if y2 is a greater y value than y1, regardless of them being negative or positive, that difference will always give you the positive height of that strip. This is. Can you see that? Does that make sense? And so therefore, even though this goes as a negative territory and then up into positive territory, we have this. We just have one strip, which is the y value of the blue function minus the y value of the red function. Will always give you the current distance between them, regardless of whether they're negative or positive. So we can just do one strip, and then what is our y2? Blue one up there. So it'll be delta x times, the blue one is x squared plus 2x minus 2 minus, make sure you put parentheses, we got lots of terms here, 2x squared plus x minus 4 and so that is the area of our typical strip. and then we got to integrate that from this x value to this x value, which we find by setting the y's equal. By setting y's equal and solving, you end up with a quadratic, and you're going to get 2 roots to that quadratic, and those 2 roots, when you set those equal, will give the x values of the endpoints of the region. And so those end up being x equals -1 and 2, positive 2. So we're going to add up all our typical strips, the areas, starting at -1 and ending at positive 2. So I'm not going to write that out again, but that's our, we're going to sum all of those up from -1 to 2. dx. Okay. So the key point here is that regardless of where that thing is, in negative y territory, positive y territory, or half and half, taking a higher y value minus a lower y value will always give you that height, positive height. Regardless if they're both negative, if one's negative, or they're both positive. Okay, other questions? Okay, so then we need to look at some other examples here. Let's look at so something like this. So there are going to be ones that you're going to use your graphing calculator for. Okay, it's appropriate because they're kind of outside our elementary functions that we should know how to graph. But you have to have elementary parabolas like this. You have to have some kind of method to sketch them on your own. And one important reason is if you solve these for y and then use your graphing calculator, and you're not careful, you won't get the right curves. All right, it won't be complete. So we really need to be able to sketch these without a graphing calculator. Okay? So one way to do that is, since these are different because we're used to y equals an expression of x's, right? So one way to do that is to flip them. So consider, so we should be able to do y equals x squared and y equals 3 minus x squared, 3 minus 2x squared. And then apply the fact that instead of, so we're going to change, like, so anyway, so let's sketch those. We also be able to sketch these without a graphing calculator. Y equals x squared. Piece of cake, right? Through the origin. Opening upward on the y-axis. And what about 3 minus 2y squared? So that has a vertex. Where's the vertex?
0 and 3.
0 and 3. And then is it going to open up or down? Down. And how will it compare in the shape to x squared? All the y values are going to be stretched, right? They're going to be stretched, so this thing is going to appear narrower because it's being stretched vertically, right? Stretched vertically. Okay, now this isn't our region because we now need to make the adjustment. What I did is I flipped x and y to get a start. So now, if that first one is at the origin, it opens on the positive y-axis, what will x equals y squared do? Open on the positive x-axis, right? So it'll also go through the origin, and it'll open on the positive x-axis instead of the positive y-axis. So that's x equals y squared. So you see how I talk through that? So if y equals x squared opens up on the positive y, x equals y squared must open up on the positive x. And then if y equals 3 minus 2x squared has this vertex of 0, 3, then where would the vertex of x equals 3 minus 2y squared be? 3, 0, right? So if the vertex of is 0, 3, and then we switch x and y, it's going to be now 3, 0. And if that one opens on the negative y-axis, then x equals 3 minus 2y squared will open on the negative x-axis. And it'll be something like that. So here's the risk. If you solve this for y, and then you put it in your graphing calculator, if you're not careful, you'll only get the top half. And that's not right. You need both halves, right? You only get the top half if you do y equals radical x and don't have the plus or minus. So in order to graph this on a graphing calculator, you need to put in two functions. And my experience is the students overlook that, and they just end up with the top half because they're using their graphing calculator. Same with the other one too. If you solve for y, and you don't do a plus or minus and have two functions, you're only going to graph the top half. So that's why it's important, especially for these x equals y squared, or x equals an expression of y, that you can handle it without a graphing calculator. Question back there? Yeah.
Yeah, isn't it like, couldn't you use the first graph we made and just reason? Like,
That's what we're doing. So you just want to reason differently.
But I mean, yeah, I guess so. But I mean,
Yeah.
like, just use all your calculations using the first one, and then reason after you do the calculations, such that we know the first graph's going to give you a positive value, and the second graph's going to give you probably 0. But if you rotated it 90 degrees like we did after you do that, it kind of seems like making the second graph could be avoided, I guess.
Making the second graph. What do you? I guess I don't know what you mean by first and second graph.
I think what it means is just like do all of the integrals for this first graph where you still have the y-axis on top, and then you would just compare that.
But what do you mean by first graph? This?
First graph is
Okay.
yeah, the one on the right.
Well, okay. So the problem with that is if this is part of a grander problem that we do later, like that has to do with volumes. So now this transfer becomes more and more complicated. So, and I could ask you on the test to make a sketch of the region defined by these two, and you need to do it. But yes, you could, if all we were doing is finding this area, then you could do the integral for these, and it would be the same area. That's absolutely true. Yeah. Is that what you were saying?
Yeah.
Yeah. Mm-hmm. Yeah, and that's true. Okay, so now how do we want to approach this problem? How do we want to approach this problem? So if we look at typical strips here, if we did a typical strip like this, and then over here we'd have a different typical strip, and then what do you see about those typical strips? The top and the bottom are both defined by the same curve. So we kind of have multiple issues with this that maybe we'd like to avoid. The first issue being the bottom and the top of the strip are both those y values are defined by this curve. And then the second issue is this idea that we'd have to break it up into two regions and do two integrals. So there's a way to avoid that. Many of you know. What is it we can do to avoid both of those issues? Okay, so far in class we've only talked about vertical strips. We've only seen these vertical strips with a width of delta x. Monday recitation people, you know that you can do a horizontal strip like this. And this makes life a lot easier. Notice that starting at the bottom all the way to the top, you have the same strip. It's the same strip. It has the left side of the strip is the blue curve, or x equals y squared. And the right side of the strip is the other one, 3 minus 2y squared, and that's the whole way. It's the whole way from the bottom up to the top. So let's do it. Our typical strip is going to be base times height. And what's our base now? Delta y is our base. It's the thin direction. And then now the height is lying on its side. It doesn't matter how you interpret the base and the height, right? Because it's a rectangle. So I'm just saying the base is still the thin one and the height is the long dimension. So this height, is it x coordinate, y coordinate, change in x, or change in y? Now it's a change in x, right? So it's going to be the x, call this x2 here. And this one x1. So we want x2 minus x1. But because it's delta y, we need to get those in terms of x, but that's exactly how we have them. x2 equals, x2 is defined by this red parabola here, so that is 3 minus 2y squared. And x1 is defined by the blue curve, so minus y squared. Yes, sir?
Is the base of your typical strip typically going to be just what you're
So-
integrating with respect to?
So that's what I chose to do. So it does. This could be the base. If you want to call this the base and this the height, that's fine.
But is that normally? I just mean, is that normally?
No, when I started doing this problem, that's what I did. So maybe you always want to think about base as horizontal and height as vertical.
Yeah.
But since it's just base times height, it doesn't matter.
I just mean, if you're integrating with respect to y, there is change in y going to be the easiest way to do the typical strip? Is it going to just be in there?
I didn't get that.
You know,
Okay, let's finish. All right, so that's our area of our typical strip, and then we're going to go from what to what. So we would need to get what? The y value of that intersection point and the y value of that intersection point. So now we're going to set x is equal, because we're trying to find out where's, at what x value are the y's equal, right? Sorry, at what? Yeah, so x's are equal. X's are equal. Okay, and so then those will be y. So we want the y values where the x's are equal. And so that would be y squared equals 3 minus 2y squared, which turns out to be 3y squared equals 3, so plus or minus 1. So y is plus or minus 1. So the first typical strip is down here at y equals negative 1, and then we're going to add them all up this way, horizontally, and the last typical strip is at 1. So it would be the integral from negative 1 to 1, 3 minus 2y squared minus y squared dy. And that will give me the area of that shaded region. So sometimes, you have a choice whether you're going to do vertical strips with dx or horizontal strips with dy. In certain problems, it'll be very advantageous to pick one of those over the other based on what your region is, what your curves are. Okay, so we'll have regions part 2 due Friday, web work. Okay?